Hello, everyone. It's a pleasure to be in that distinguished audience. I can't see everyone, but I'll try my best to connect with you through my talk. It is by no means I can take credit for all that work myself. I work with a group that is working on very diverse topics. Today I'll be presenting our work on learning symmetries from first principles with machine learning, and you can see the list of my collaborators, a little bit more about it in a second. So there you go, the first snag. Oh yes, it works. I was worried that it's not going to advance. So today actually I'm going to be talking about the first of a series of papers that we have. The first one is the deep learning symmetries and their Lie groups in algebras from first principles. Is precisely the title of the talk. We have several subsequent papers, application of this algorithm on actual database, and perfecting actually the algorithm that we have developed and demonstrating on a variety of groups going all the way to the exceptional groups, the G to F4 in E6, which is the paper currently in review. So here we are, as I said, by no means I can take credit for all that work. Thank you for the organizing, for reaching out to us and to present this work of a wonderful group of people. Here is my main collaborator, Konstantin. He's a faculty VO from the physics department at the University of Florida. We are both faculty in physics. Our students, Alex Roman, who graduated actually this year, and our current students, Roy Forestano and Iup Unlu, which are starting their third year in graduate school, and they have integral part of all that work. We also have one of our postdoctoral fellows working on this project with us. As you can see, we are in sunny Florida, so if anybody wants to visit Florida, more than welcome. This is the way it looks in January, keep in mind. So this is really a fantastic place to be. So we actually, I always try to advertise that we are very, very diverse group. We have diverse expertise from expert programmers, which are our students, and they are of course learning the ropes in physics, but they came in with excellent programming skills, to expertise in particle physics and theoretical physics and statistics and application in a variety of fields. And myself, I'm an astrophysicist. I actually work on detection characterization of extrasolar system planets. So as you can see, this expertise, diverse expertise of the group members is very fruitful for the type of interdisciplinary work that is involved in application of machine learning in different fields in science, or in this case in mathematics actually. So more about the talk today. I'm going to be, as I said, we're going to talk about symmetries. We're going to start with symmetry in everyday life, in math, in physics. My formal background is not in group theory, so I thoroughly appreciated some good background in group theory when I was looking at papers to start this project. So I will start with a little bit of introduction, the beginning. So I was not sure what is the background of the audience today, so I do have some background information on that. We will be talking mostly about continuous symmetries, actually exclusively about continuous symmetries, which our work is on rather than discrete symmetries. And I will demonstrate our method on a variety of examples, starting from the orthogonal groups in 2, 3 dimensions, 4 dimensions. We'll see if we have time for something more, because those are already a full plate of things to look at, as you will see. All right, symmetries. This is beautiful things. If you ask people on the street what symmetry is, they will probably most likely relate to some like their experiences in nature. The most common one that people give an example is the symmetries in snowflakes. Those beautiful symmetries. You can see the axis here. Typically, we have 3 different. hexagonal, the snowflakes, although there's some exceptional ones like 12 with 12 branches. And actually, if you didn't know, those are considered lucky ones. So similar to the 4-leaf clover, the 12th branched snowflake is considered a lucky snowflake. So keep it in your hands until it melts. We have, of course, other many examples in nature where we have a demonstration of symmetry. Here's the butterfly. We have the reflection symmetry here. As a matter of fact, there's a lots of publications that are emphasizing that symmetry and the simplicity spontaneously emerge from algorithmic nature of evolution, and kind of illustrated by almost all things that we see live. They exhibit some kind of symmetry, whether it's bilateral or whether it's radial symmetry, but most of those symmetries seem to be discrete symmetry. So the check mark here for the talk is we will be talking about continuous symmetries. And here are some examples of shapes, and that you can see those continuous symmetries where if you rotate the object and any angle, this still is going to be identical to before. Of course, some other pretty pictures for you to enjoy and actually recognize that those things are symmetric. Again, what is actually symmetry? If you, as I said, if you ask a person on the street, they will start, wow, it looks the same. It looks the same, but in what sense? This is where mathematics comes in, where the subject of symmetry is more rigorously formulated and placed in solid ground through definitions and mathematical formulas. All right, so symmetry in science. So in terms of math, the term symmetry is really used to refer to an object that is invariant under some kind of transformation. Actually, this is a quote from Wikipedia. Interesting enough, Wikipedia became a very good source for information for us working on the subject of group theory. Actually, that's a really good thing, because usually difficult subjects are presented in very digestible form on Wikipedia, and we took advantage of that. We do have some references to information that is posted in Wikipedia. The key part of this definition is highlighted here. We have an object and there's a transformation that's being acting on this object, and something stays invariant. So this is kind of a more generalized view of symmetry. And of course, in more narrow sense is what we see in the examples of the snowflakes. The object is a snowflake, it's a visual, you can see it, you can imagine it. The transformation is just a reflection of particular rotation, and what stays the same is the shape of the snowflake, it looks the same. In terms of physics, it's argued actually that physics is a study of symmetries in nature, and from no one less but Phil Anderson, a Nobel laureate. Of course, this is a very general statement, but digging deeper into that, you'll find that symmetry is really essential in physics. And a famous theorem, Noether's theorem from the turn of the century, is actually embedding that every continuous symmetry of an action of a conservative system has a corresponding conservation law. So the conservation law in physics, they are the cornerstone in physics, basically, are associated a particular symmetry. For example, a symmetry of rotation is associated with conservation of angular momentum. The space translation symmetry is associated with momentum, and the time translation symmetry is associated with conservation of energy. Those are cornerstones in any physics theory. Of course, just the consideration that we consider the universe homogeneous and isotropic is also fundamentally a statement of symmetries. So here we go. Some basic things from a group theory, which we are going to use and we are using in our machine learning algorithm is really basically definitions. This is all about as you need to be able to develop the algorithm we do, and that's why we call it from first principles. We don't require any more knowledge than the basic definitions and the basic properties of a group to discover different groups in a data. So we to a group we're going to call a set of elements G, on which we have a defined binary operation, and there is a set of requirements of that operation. We have a closure. In that sense, if you have two elements of the group G, after the operation, it results in another element of the same group. So this is all. This is what the closure means. So it's inclusive of all those elements. We need an element that is a unit element, or in other words, do nothing element. That is part of the group. We have inverse element, or that also is part of the set. In terms, that would be just reverse the transformation that you have done. And we also have associativity property associated with these elements. Note this associativity property is on the transformations rather than on the objects that we're acting upon, because sometimes this is not a property of the object on which we act, and we have some examples. Now, this is mathematically basically almost all we need in order to construct an algorithm to find symmetries in data. In physics, and I would subscribe to that group of scientists in physics, we have a little bit more loose kind of approach to a symmetry. I wouldn't say loose, but more pragmatic or more example-based approach. It might be less abstract. So this we define the transformations more explicitly. For example, we say the U3 is a group of transformations represented with a 3x3 unitary matrix. Note that it doesn't have to be necessarily a matrix representation, but since rotations are very often represented with matrices, we would say we would have a matrix representation for the group. We sometimes instead of defining the group through the transformation matrix, we can define it through the conserved property or the invariant that the symmetry preserves. And for example, we would say the O3 is a group of transformations preserving the length of a 3D vector. So in this case, we define the symmetry through the preserved parameter, or what we call the invariant. We're going to label it afterwards a little bit differently, but in physics or in math, we call it the invariant property, which defines the symmetry. In this case, we define the symmetry through the type of transformation that we're dealing with. So those are two different approaches that we're going to take advantage as we work through that presentation. All right, so this is all the group theory you need. You don't need any more introduction. But now I'm going to give you a little bit of an introduction. How do we approach the subject from machine learning point of view? And I think this bridge between the sciences is really important so that people can talk to each other and understand each other. Because what we kind of face is kind of a gap between the rigorous mathematical representations in group theory, how they're phrased, and all the definitions that are buried in the language, and then translating that into machine learning terms. So it is very good people to be able to talk to each other in terms that are meaningful for all the groups, all the people in the working group. And for us, that has been essential. As I said, we are a very diverse group of people, very diverse expertise, and being able to understand each other what we mean by saying a group, or what we mean by saying features or invariant or neural network has been very essential in order to be productive. So here's that translation map. We're having some mapping here to do between the different fields. So in sense, when you work with symmetry, we actually start with the vector space. So this vector space could be a data set. I mean, actually it is a data set. Could be an actual data, images. We actually done some work on the MNIST data set, which is a collection of images of handwritten digits. But it could be any data set. For this talk, we are using really synthetically generated data set. That means we just take points in the vector space, literally generated in a fraction of a second. And this is our starting point, the vector space on which we act with the transformation. Note the color coding here. The object is the vector space or the database on which we start working. It is acting upon a transformation, and here it can be described as a matrix in mathematical sense. And this matrix or this transformation transforms the input vector space into a new vector space, note the prime here. And we would like for the symmetry to be true symmetry, some kind of property of this vector space to be conserved during that transformation. And that property is typically a polynomial that's a function of the vector space. And as you can see, this phi of x equals to phi of x prime is defining the symmetry. This is the oracle. We're going to call that oracle, but in machine learning terms, that's a very often used term. But this is the invariant. This is the invariant function that is being preserved. In the sense of the snowflake, we say the shape is preserved, like looks the same. This looking the same is precisely that, that expression written mathematically, the oracle or the invariant that's being preserved during that transformation. So, and that could be very abstract. That could be, in simple terms, we're going to see in the examples that we have, a length of a vector, or it could be a normal vector, it could be a variety of different things. It's really up to the user to define what is the conserved quantity. Of course, if we are to look for a particular symmetry like O3 or SUN or one of the special groups, they have a specific invariant that's being preserved, and enforcing that invariant determines what symmetry you are gonna find. Okay, so this is the mathematical setup, and let's see how that looks in terms of machine learning. We have the color coding here. Since I'm not in the audience to point to the screen, please do follow the color coding. The vector space right here, it is right here. This is our database. This is individual points with in an n-dimensional space. We have a vector with n components, and we have m samples or m points in this n-dimensional vector space. If you have, say, three-dimensional vector space, you're going to have 1, 2, and 3, and you have 1,000 points, you're going to have 1,000 points right here. So that would be the input vector space, or your database for that matter. And this is usually called features in machine learning. These are your data that you're working with. The matrix or the transformation that is being performed on that database, on those features, is actually a neural network, here the blue square, that performs a transformation on the features. And what we want to preserve is the so-called labels, or the calculated function, the values of the calculated oracle that we have right here. All right, again, vector space, we act upon with the neural network. The transformed vector space needs to preserve those labels. And this is the machine learning setup that we are working with. Okay. All right. So here is an example, again, a parallel example between a, I would say, linear algebra approach and machine learning approach. Again, X is your input vector space. X prime is the transformed vector space. And we have our transformation. I is the identity matrix and G is the transformation that we have. We are working with, again, with the continuous symmetries. And here we have a small parameter epsilon, a favorite, sorry, a favorite letter for infinitesimal parameter in mathematics. So it's kind of universally used. And this ensures that we have small transformation to ensure that this is a, we are actually dealing with continuous symmetries. Okay. Analogous, this is the machine learning approach. We have the input vector space, so the data, the features in the previous view graph. We acted upon with a with the neural network, and and here we have the transformed vector space. Here is a particular visualization example. After our algorithm, which I'm going to explain in the next few view graphs, we're going to be looking for we're trying to find the generators right here, G, for the generators of the transformation. And the generators are shown here. This is just a particular example for the SU3, which is a group in the complex space. We are expecting to see complex generators that are representing the SU3 group. And here we have complex generators. So I'm going to spend a little bit of time here just because we're going to see lots of those figures afterwards. Each square that you see right here is a matrix. This is a 2 by 2 matrix. Each element is color coded. Here you have the color bar. The white represents to a value close to 0. And we have a positive values in blue and red for negative values. Here we have the real part of a complex matrix. And here we have the imaginary part of the complex matrix. If the matrix is just real, we're going to show only the real part, and we're not going to bother to put a imaginary part. But this is a complex generator, and we have the SU3. We actually have something known as the Pauli matrices used in quantum mechanics in physics. And we have 1. This is 0, 1, 1, 0. This is 0, 0, 0. This is -1, 0, 0. Oh, sorry, clicked 0, 1. Here is 0 real part of the generator, and you have here 0 minus I. This is a complex, and I 0. So this is the well-known Pauli matrices. Okay, so this is in matrix form representation. You're going to see a lot of those just to illustrate which group we have identified. And here, when we're dealing with a nonlinear case, because this is an example for linear transformation, when we're dealing with nonlinear cases, we're going to have a picture that shows you space. This is a two-dimensional input space. X1 and X2 are those the two coordinates in the vector space that we have. This is a two-dimensional input vector space. Phi is our oracle, is color-coded. So the color that you see here is the value of the oracle. Remember, we're looking for symmetries. That means the oracle is preserved under transformation, and basically the contour lines in this figure is showing what is the direction in which the oracle is preserved under, and the arrows is the result of this vector field that you see. The arrows is the result of the found symmetry. So again, the color code that you see is the value of the oracle, and the arrows are pointing the direction in which if you transform the input field X, the value of the oracle is preserved. So in other words, we want those arrows, the find transformation, this is the arrows presenting the found transformations through the algorithm, to follow the color, to follow the contours of the color. If the arrows are crossing the counters, that means our symmetry is not a symmetry. The thing that we found is not working. So if the lines are following the counters, that means the found symmetry is the correct symmetry. We successfully find the symmetry. So as you can see, this is a linear case and this is a non-linear case. In the linear case, we successfully can use actually even the linear algebra approach, but the neural network, basically a shallow neural network that has only one layer, is equivalent to using a matrix linear algebra approach. So you're going to see lots of those things on the left and a few of those on the right, because we're going to see mostly linear cases in this example talk. I hope that was informative. Now, arguably, the most important part for finding the symmetry, not finding the symmetry, but to define the symmetry, is the oracle that you use. The different symmetry groups have different oracles depending on what vector space they are defined and exactly what is it that you want to preserve. So here's an example for the ON groups. The oracle is nothing less but just norm 2 of the vector, and this is in real space. So the rotational, orthogonal rotational groups, these defined on the real space. We'll see some example. This is nothing else but really rotation in normal space. The U groups, the unitary groups, are very similar to the R groups, but they're defined in the complex space, and we have, again, the norm of the vector is preserved. This is what we want to preserve under the transformation when we're looking for that transformation. All right, here's an example for the SO13. This is the Lorentz group, which is a little different than the O groups. I'll show some examples of that. Has the Minkowski metric for an oracle, and again is defined in real space in general, but we have to preserve that. Here's some example. We're going to see an example of a squeeze map oracle, which is basically multiplication of those two elements in the vector, in the input vector space to be preserved. Here, example of much more exotic type of groups, which is the exceptional groups. G2 has not one, but two separate oracles. This is actually our latest work on the exceptional groups. Here's an example for the oracle for the G2, and this is F4, which has 3 oracles. So we extended our original work that works with a single oracle. Basically, the oracle is a scalar, returns only one value. And without much of a trouble, we were able to generalize that to more than one oracles to be preserved. So basically let me just go back. Instead of having only one column here, now we have many columns. The algorithm works perfectly well, even if you have more. This is the oracle, the preserved invariant is not just a single value. You can have several of those constraints imposed. Okay. And those are actually imposed on octonions, which is a very different from the real vector field. The very big leap from the real numbers to go all the way to octonions. It took quite a bit of progression in my understanding of group theory. Okay, so in my personal opinion, and probably lots of other people working in the machine learning field, arguably the most important part of success or not success of your algorithm is your loss functions. It needs to be the loss function. I'll tell you what we mean by that. Maybe lots of people in the audience are well familiar with that, but I don't want to risk people not being aware of what the loss functions do. So how does the machine learning algorithm actually learn? Well, the answer is by minimizing the loss function. It is actually a minimization problem. And the loss function incorporates certain constraints that you want your algorithm to satisfy, your output to satisfy. You want to achieve something, and that's what we want to achieve. These constraints incorporated in the loss function, and that ensures that your result actually satisfies new criteria and it works. For example, if you want a function A to be equal to a pre-calculated value B, and you have some variable parameter with which this function is dependent, and this is your constraint, you want that function to become equal to B, then your loss function is going to look something like that. The difference between your target, which is B, and your variable that you vary throughout the process, your calculated value that you change throughout the process, you want that to be minimized, that difference. And here you have a loss function. You minimize that value in order to satisfy that condition. So this is a very simple example of what the loss function looks like. The most popular minimization algorithm that is being used in machine learning is the Adam optimizer, and this is exactly what we use as well. Now, what are the constraints that we use to find the symmetries or the groups, symmetry groups that are present in our data? We don't use any domain knowledge. All we use is the definition of groups. Again, nothing more than what I presented a little bit earlier as properties of the group. The most important constraints we have is the invariance. We want to preserve the oracle, or we have a properties that are being preserved through the transformation. So the invariance is the number one requirement or constraint in our loss function, which basically looks very much like that. I'll show you in a minute. Then we have a normalization constraint that ensures that our transformation is not trivial, because doing nothing also will be resulting in invariant transformation. Doing nothing is also a result of resulting in invariance, but we do not want to do nothing, we want to do something. So it ensures that what we find is a non-trivial symmetry. We have an orthogonality requirement. We would like, in other words, we want the symmetries that we found that are different from each other. We do not want to find the same over and over again. We want to have a distinct, each symmetry that we find, each matrix that we find, each generator to be distinct. We have a closure condition. This is the closure condition for belonging to the group. So all found symmetries to form a group. And something that is not part, sparsity is something that is not part of the definition for group, but you will see the usefulness of this one. We actually originally did not use sparsity condition, but after scratching our heads for a long time, what we are finding, we realize that it's extremely valuable to have the sparsity, and I'll show you in a few minutes what I mean by that. All right, now all those words are put into action. This is our loss functions. This is the different, again, invariance, normalization, sparsity, orthogonality, and closure. For those of you that are very interested, I'll be happy to discuss those in details afterwards. But you can see this is nothing else but working with matrices and defining those conditions in mathematical form. Here is our invariance, the most important loss function, which basically states that after the transformation, this is our oracle, the oracle acting on the transformed vector space and the oracle acting on the original vector space. Their results are minimized, the difference is minimized, and this is where we require this loss function to go as small as possible. Keep in mind, this is computational mathematics, as I call it, experimental mathematics. This never goes to zero, but we get to machine zero, like things like 10 to the minus 15, which we're very happy with this kind of results. And then we have normalization, sparsity, orthogonality, and closure conditions. It's lots of mathematical terms here. If anybody's interested, I'll be happy to discuss those. I like that visualization because we literally stack those individual terms as like sausages in our global loss function. We could put some weights in front of those terms, depending on how the training goes. If we do not want any of those terms to be dominant and to pull away from the others, because sometimes those, in order to minimize the entire function, the algorithms are trying to pull to one or to the other more, depending what computationally gives you more favorable outcome for the minimization. So sometimes we do have certain what we call hyperparameters or weights in front of those sausages, each of the sausages, in order to make the outcome balanced in terms of training. All right, now this looks more like what the machinery looks like. Here we have a data point sampled from a normal distribution, or could be just your data. This is the data that you're dealing with. This is X. This is the, in our case, this is a synthetic database. This is vector sampled from, for example, from a 2 or 3 dimension. The examples that I'm going to have is in 2 and 3 and 4 dimensions right here. This is a vector space with its components. Okay. And this is what enters the machinery. We also have a few other inputs. These are the other inputs. Of course, by defining our vector space, we know the dimensions in which we work, 2, 3, 4, 5, 10, and so forth. There's no limit here on the number of dimensions that we want to work with. Then we specify how many generators we're looking for right here. And here we have some tolerance within our error bars at the end. So this actually, what happens afterwards is the machine learning algorithm gives you a suggestion for generator. This is the suggested generator. This suggested generator is actually our transformation, acts on the incoming field and gives you a transformed vector space. Here's the original vector space. This is the transformed vector space. Oracle is calculating the value of the original vector space in a value on the transformed vector space. And that is being fed into the loss function to calculate the invariance. This is the most important loss that we have. How close those outputs are, that determines the biggest part of the loss function. On the other hand, we take these generators and also we perform analysis of those, whether they're normalized, they are orthogonal, and do they satisfy a closure condition. And if the answer is yes, and the loss is very small, we are ready to have a readout, and we look at what kind of generators we have that satisfies this invariance condition, or we found is symmetry. Now, if that's not small enough, we're not happy with that, the system is not satisfying our value for happiness, or for that we're satisfied with the value of the loss function, this is fed back to generate a new set of generators, and the process continues. And that is done many, many times. And through Adam Optimizer, we're converging to a satisfactory, to a readout that gives us the result of the search. Basically, this is a search through the generators that would satisfy the invariance condition and all the individual requirements that we have on the generators. Okay, so this is basically the machinery. Here's an example. This is a 2D example. That means our input space is 2-dimensional. We are talking about we are working in real space here. So we're having a rotation in 2 dimensions, something like that. Okay, here's my demo. In 2 dimensions, our algorithm, this is what actually it's basically looking like. Our oracle is preserving the length of the vector, right? This is the oracle that we're using, preserving the length of the vector. And if you have to color code this oracle, it's nothing else, but as you can see, this is actually 0. The red here is 0, and it's increasing as you go away from the center of the coordinate system. It's nothing else but marking the distance to the origin of the coordinate system. Okay, this is what it is. Now, we have right here is something that all people working in machine learning always wants to see when you submit paper in machine learning journal, they always want to see how's your loss doing, how's your loss function performing as you go through epochs of training, how many times basically iterations you go through your calculations. So we have experiments here with choosing the number of generators for this two-dimensional space. We have an experiment with one generator. We have experiment with searching for two generators. And let's see what we actually got here. We have two loss functions. The blue one is associated with searching for a single generator only. And as you can see, the loss function was going down and down and down, and goes to 10 to the minus 14. It reaches machine 0. We have successfully found a single generator, which is nothing else but this axis of rotation, right? Single generator. And this is what is actually illustrated in that figure. This is a very trivial example, but you have to make sure that the trivial works before you go to complicated things. So this is our two examples for the algorithm. However, when we want to find, well, we know that there is one generator. What about two generators? Can the machine find two generators? I mean, I surely cannot think of two, but maybe the machine can find two generators. So here we ask for two generators, and the machine works very hard for 600 epochs and converges, but it converges the loss function to a very high value, which tells you it did not successfully find two generators that satisfy the loss function and make the loss function small enough. Sure, it gave me something, generator 1 and generator 2. But the loss function for these two generators is very big. What does it look, why those two generators did not work? Well, just a brief inspection will show you that looks very much like that one, right? It's basically more or less the same. So why it doesn't work? Well, the reason it doesn't work gives me two generators that are basically up to minus sign. They're not different. Those two generators are actually not orthogonal. So these generators, they do not satisfy the orthogonality condition. They satisfy the invariance, that's fine, but the orthogonality condition is not satisfied, and therefore those are not unique generators. That's the whole point. So again, looking at the loss function, we've been staring at lots of loss functions to see if we find or do not find generators that work. Again, this is a fail simulation. This is a successful simulation. Let me see how I'm doing on time. Okay, very talkative. Okay,
can I ask a question?
Sure, but you have to speak up.
Yeah, so rotation is generated by one matrix. I mean, what's the implication of this? It's a little bit confusing.
Yes, thank you for the question. We are doing here two examples of how the algorithm works. We are not in a discovery mode, we are in demonstration mode. So the idea is, we very well know that we have in the 2 dimensions, we're going to have a single generator in the O2 group. Okay, we have a single generator, and that is expected. Now we want to see if the algorithm is going to find it to begin with, and yes, it does. The loss function goes to a very small value, and we say, well, can it find two? Well, how do we know that the machine is not going to find two, and then we're going to say, well, there are two generators. The machine finds two generators, but they do not satisfy the loss function to the loss function. The loss function stays high.
So what's the one generator we found here?
Yes, a single generator is found.
What's that?
Oh, this is the matrix form. This is 0, 1, -1, 0.
I mean, the implication is that matrix generates rotations. Probably
yes. This is the only thing. This is precisely that. That's because it preserves under rotation. We preserve the length of the vector. This is the symmetry we are finding because we impose the length of the vector to be preserved, and our vector space is centered in the origin of the coordinate system, so we don't have translation. Does that answer your question?
Okay, I'll think about it. Yeah, thank you.
Sure, no problem, no problem.
0, 1, -1, 0.
Yes, yes. So the colors again are the scale. This is 0, 1, -1, 0, and this is the rotation that we have. Okay, so let me show you a three-dimensional case. In the three dimension, this is basically looking at the SO3 group. And we have an example, different, again, focus on the loss function right here, loss function. And we have experiments that say, can I find a single, can I find a single, and this is blind search, this is not guided. The only thing I ask is how many generators I'm looking for. I'm looking for single generator, and I see a successful find for single generator. Then I say, well, can I find two generators? Oh, wait a second. I actually cannot find two generators only. It actually fails that training for two generators. Then we have, I'm looking for three generators, and sure, I find three generators. I also, I did not find four generators over there. So for people familiar with the SO3 group, they would know that these are the expectations. Basically we're demonstrating that the algorithm that is a machine learning algorithm, which is based on first principle search through the data, finds the expected theoretical predictions. And the theoretical predictions are really are indeed that we have a subgroup with one generator and we have the full group has three generators. SO3 has three generators. Okay, so here are the three generators that it finds. And all right, I mean, looks like three generators. What do they look like? Looks like colorful blocks. Again, these are matrices. Each color corresponds to a value. So you can see we have three generators. They look very colorful, very pretty to show in a talk. But really, I'm kind of lost with those looking at them. Well, the first thing you notice, there's certain properties that they do, and we expect from SO3 generators. They are antisymmetric. So you can see, although they have a variety of colors throughout, they're sure antisymmetric, and that's expected for the rotational groups. And we have the diagonals, which are 0. Okay, we have a 0 trace right here. The diagonals are 0. So indeed, those satisfy those expectations. Keep in mind, we did never actually specify those in the loss functions. They came up out of the search. So the only thing that's imposed in the algorithm is are the losses that I showed you. There's nowhere in the losses that says that this has to be antisymmetric or symmetric or whatnot. Okay. So in the beginning of the training, we have some random orientation of the suggested rotational axis, and this results in a very high loss rate, loss function. By the end of the training, those axes are perpendicular, and it finds the correct orthonormal vectors. I see that I'm a little bit short on time. I guess I stressed the introduction a lot, but I'll show you some 4D rotations. See rotations in 4 dimensions. We're looking at the SO4 group. Here's the loss function, experiments for different number of generators. And again, we do know the theoretical expectations because we understand group theory to that extent. And the algorithm successfully finds the number of generators that that are shown here. The 2 generators, the 3 generators finds well the 3, 4, and 6, but there when it comes to 5, does not find 5 generators, and stops at 6, does not have 7 generators. Here examples of the generators that it finds. This is actually a subgroup of SO4. This is a 2 generator group. This is a subgroup. Actually a abelian subgroup, and we have a abelian subgroup. Those 2 generators actually commute. Again, the properties, we have a 0 on the diagonals, and they are anti-symmetric. We have this is another subgroup of the rotation in 4 dimensions. This is shown here. And we have for the 4-dimensional generators, This is non-abelian. I mean, the ng equals 3. This is a non-abelian example that shows the structure constants right here. And we have a for 4 generators, again, 4 generators composed here. They all show the expected properties, but they're difficult to they're very difficult to decipher. It's just looking at pretty pictures, difficult to understand. Again, this is the full group with 6 generators. This is the maximum. This is my timer, I guess. This is the maximum generators that we have for that for the SO4. SO4 has a maximum of 6 generators. And although they satisfy all those individual properties, and the loss function is practically machine 0, they're difficult to decipher. And for us to to convince that those things actually do work well, took us lots of head scratching to digest those values. So here is a summary of experiments that we've done. This is on this what we call a skyscraper plot, because it resembles very much a sunset, say in New York or Chicago, one of those big cities, and we call the skyscraper plot. We have on the vertical axis number of dimensions of the input vector space. This is up to 5 dimensions that we look, and looking the results of the search for different number of generators. The red colors means the loss function was close to 1, or this is a log value of the loss function. And the blue colors, this is 10 to the minus 14. So this is successful trains. So these are the squares show the successful found symmetries. This is in agreement with group theory. Here we have an example of 10 generators, an SO5, for example. The maximum number of generators for the SO5, and the all unsuccessful trainings for the red one. And they're all, every single one is in agreement, of course, with the current understanding of those. And voila, here we have an important group for physics, which is the SO10 group, which is a cornerstone for some of the ground unification theories. And without much of a sweat, the algorithm can find you what is it, 45 different generators. They all look beautiful. They all have satisfied the condition that there's zeros at the diagonals, 0 trace, and they're anti-symmetric. They also satisfy every single loss term in the loss function. The only thing is just you look at them and you're like scratching your head and don't quite understand. In order to tackle that issue that they're not very explainable just by looking at them, we impose the so-called sparsity condition, and I'll go on that one to show you. Remember these colorful plots, similar to the SO10? We impose a sparsity term in our loss function to encourage to find the generators out of all the possibilities that it can find. Remember, those are not unique. To show us the ones that actually have more zeros. And if we impose that to maximize the number of zeros in the matrix, we actually have very well interpretable and understood representation of those generators, which are much more easily interpreted. And this is what you see in the textbooks. You never see in the textbooks anything like that. This is just one of the many possibilities. And in the textbooks, you see something like this, which shows you, again, one of the many possibilities. It is just the one that is much easier to interpret and print in the textbooks too. Okay, I see that we are very close to exhausting my time. And I want to show you some, because I showed you lots of linear examples, I want to leave you with a situation where we have a highly nonlinear situation. Here, the oracle is discontinuous. Remember, the colors here represent the value of the oracle. This is in 2 dimensions. The colors represent the value of the oracle, and the goal of the algorithm is to actually align those arrows, to align these arrows along the contours of the color. That would mean that the algorithm has found a symmetry. As you can see in this case, in the linear approach, we are not successful of finding that symmetry in the data. Again, the data is the colors that you see here, and the arrows is the suggested symmetry transformation, which clearly does not work in that area. This, if you do actually do several experiments, sometimes it's going to work here, not working here, sometimes it's going to work here, not working here, but does not work on the entire domain. And this is for shallow neural network, which is equivalent to using a matrix linear algebra approach. Now, if you use a three-layer hidden, only three actually, hidden layers in a network, which would call a deep neural network, but it's not all that deep to begin with, just three hidden layers, you see that change from here to here. If you look closely, the arrows, which is the found transformation, follow exactly the contours of the color, both on the left and the right side of the domain. Very successful training. And in the discontinuity here, you can see the arrows became small. They actually, the transformation is 0 right here. Very successful training. And this is the challenges when you have a discontinuous arcles like this one, how to find those. And with that, I will finish. As I said, we have a series of papers that we have done. What we accomplished is, by given a data set, we are able to find, if they exist, of course, a symmetry, algebra or subalgebra with a given number of generators, if that symmetry exists. If it doesn't exist, we do not find them successfully. Of course, we don't invent the symmetries if they don't exist. Some observations is, this is very stochastic in a sense. You will find in terms of finding the generators, you're going to find if, for example, for the SO, for the U of groups, you're going to find in these vector spaces every single time you run the program, you're going to find a different set of generators. So one has to actually fix the seed, the random seed in your program to reproduce some of those. So fixing the seed is very important in those experiments. Now, this training with large number of generators starts becoming slow. And that is a bottleneck in the algorithm, which we have actually tackled in our subsequent papers. And now we have much faster working algorithm that can work in very high dimensions without slowing too much. Otherwise, searching through the generator space becomes slow. So we have addressed that with the speed. We have also addressed the change from this very pretty and colorful pictures to very much more informative sparse forms on the generators. And this is our last paper that we have worked on the exceptional groups, which are defined on octonions and are important for high-energy theoretical particle physics grandification theories. And with that, I'd like to thank you, and I hope did not overstay my time. I'll leave you with all the papers. And for those that are interested to try this algorithm, we have our Python code. Students have posted that code on the GitHub page, and feel free to contact us if you have, if you'd like to run it and like some guidance on that. So conclusion, experimental math is lots of fun. That's what I call it, experimental math.